All right, so here's section 9.2, estimating the values of a parameter. And we're focusing in as we look at this is our last unit we're covering. We just got done doing confidence intervals and hypothesis testing with 1 and 2 samples for proportions when we're looking for the true proportion of the population to estimate what those were. And here now, in this case, we're doing the same type of things, but instead of having our point estimate being proportions, it's actually being means. And so, we're trying to make estimate what the confidence interval for today is, what's the confidence interval for the true mean mu of a population. So in that case, what we end up doing is we use a sample mean to kind of help us create what the potential confidence interval is, where the true mean would be for the population. So as we look at our goals is to find a point estimate, state the properties of it's really a t distribution. Don't worry about this. Our textbook calls it a student's t distribution. Don't worry about that aspect. It's pretty much in most other books and literature. It's just listed as a t distribution is all it's listed as. So that's really the only thing you got to focus on. Determine what the t values are. I'm going to show you 2 ways to do that. One is with a table, and the other is using the calculator. And then we get to construct and interpret the confidence intervals for a population mean, and then also calculate the sample size. What is the minimum sample size in order to get a certain margin of error for a certain confidence level or confidence interval. And so some of that stuff we've done already before. So it's just changing in some of the formulas and some of the process, just a smidge. For our point estimate for the population mean, remember the goal of statistical inference is to use information obtained from a sample and generalize the result to the population being studied. As with estimating population proportion, the first step is to obtain a point estimate of the parameter. In this case, the point estimate for our population mean mu, that is our population mean. We're going to use for our point estimate. We're going to use. It looks like I got cut off. The sample mean, which happens to be x bar. Looks like it didn't come through on the. Oh, never mind. It's right down here. This first paragraph, we can go ahead and just kind of duplicate it. I see as I was trying to cut and paste. So just a reminder, if they don't give us the mean and the standard deviation of a sample in a problem, typically what they'll do is they'll give us a set of data, and we have to go through and figure out a 1-var stats. So we need to go put this stuff into L1 and then do a 1-var stat so that we can go ahead and grab what x bar is. Also a good idea to go ahead and grab the s sub x from that screen as well, because if you're doing stuff by a more traditional approach or classical approach of using formulas by hand to calculate it, then you want to go ahead and grab it at the same time. So I'm going to go ahead and put this data in there because we're going to use it eventually. So let's take a moment here and get into a calculator. There we go. And I'm going to go. I'm going to get into the stats, edit, and go into the column 1, and I'm going to type in those numbers real quickly. That way I can get it. Again, we're going to need it eventually, these numbers, because as we look at some processes for checking for conditions, we're going to have to graph to see, is this data skewed? Is it, are there any outliers? So that's why it's not a bad idea to go ahead and put it in here. That way we have it for later on in the lesson. And let's see, 32.5. And I'll probably split this video up into two videos just to make it a little bit easier to watch. The second video will be more of the practice problems is what will be in that second video. Almost got it. All right, there we go. It looks like I got everything 4x4, 16. Yep. So I'm going to do a 1-var stats on this column. And we're going to say that x bar, again, we try to grab at least 4 decimals as we go. This one was only a one-digit decimal, so we're okay on there. Again, let me get my pen tool going. That's equal to 28.1, and my s sub x, good idea to get this one too, is 2.3799. Just in case we need it some other time down the road. So there's my point estimate, x bar. So now we get to talk about what is the difference between a t distribution and a z distribution. Again, when we're doing proportions, we were doing a z distribution. We were doing our standardized, kind of approach using z-scores to do it. And so a t distribution resembles a z distribution. The differences is it's based on the counts. So the smaller the n value, your sample size, then we actually have this kind of mound-looking thing, is what ends up happening. And so as we get n to be bigger and get closer to 30, we start getting closer and closer to the shape of the z distribution of that nice bell-shaped curve there. And so that's why, with that in mind, we know the z distribution is a special case of a normal distribution with a mean of 0, standard deviation 1. The t distribution is similar to it, but it's sensitive to the sample size. The smaller the sample size, we got some issues with it. So here are some properties of the t distribution. The t distribution is different for different degrees of freedom. And that's a new terminology. What do we mean by degrees of freedom? That dictates what our, what we end up using for our t-star and our formula to calculate things. A t distribution is set around 0, and it is symmetric about the 0. So the mean 0 is in the middle. The area under the curve is still 1. And then even the left and right halves. On the left side of 0, it's going to be equal to half of the area, and the other half is the other half. So I'm going to put a 1/2 in there. Didn't like the cut and paste. As t increases or decreases without bounds, meaning as I go out to the left and the right of my graph. So if I go up here, as t increases, what ends up happening is as I increase my curve here, as we go out to the side, we get closer and closer to the horizontal axis, but we never really touch it. That's what that's referring to. As the t increases, then we get closer and closer to the far outside edges. The area in the tails of the t distribution is a little bit greater than the area of the tails at a standard normal distribution. So typically what you end up seeing is, if we were drawing this by hand, not by computer, here is probably one of the better ones for a z distribution. And if I was going to draw a t distribution, basically what it is there's more space there. There's more vertical space or distance up and down below the curve. There's more area in the tails. That's what it's talking about. So therefore it's when we look at percentages for for things to happen, like especially with hypothesis testing and another section coming up, there's a greater area out there. So there's a greater probability of things occurring in those sections. As the sample size increases, the density of the curve gets closer to the standard normal density curve. So that's this first picture. As t increases, I start getting closer and closer, resembling the standard normal curve is what ends up happening. So now, how do we go about, and the reason behind that is because of the law of large numbers. We talked about that in a previous section. Now, how do we find the t-values? You have two options. You can use this table here, is what you can go through and use. Or you can use the calculator. Now, the challenge with the table here, I only got part of the table here just to give you an idea here. The left-hand column here, that's our discrete degrees of freedom. And so with that in mind, so df is our degrees of freedom. And what we do here is, in order to calculate what is the degrees of freedom, the degrees of freedom is equal to your sample size minus 1. And it's minus 1 because we're dealing with one variable here. There's other type of testing and different processes that require you to subtract 2 and so forth. But in this case, we just have to subtract 1. So as we look at what's going here, depending on what our T star is, and again, it always depends on what kind of confidence interval we're dealing with. We would still do the same process of taking our percentage, subtract it from 1 and divide it by 2, and that would give us some of these numbers up here is what ends up happening. For example, this column right here, I'm going to go ahead and circle it. That column right there, that's associated with a 95% confidence interval is what that's associated with. This column right here is a 90% confidence interval. If I had the whole page displayed, we'd actually see it at the very bottom row here. What they end up doing is we start after 30, we can kind of go up to 40, and then it starts skipping, and it does 60 and 80 and 100. It doesn't do every number here, because what ends up happening is as we get as our sample size gets way bigger than 30, we start approaching normal is what ends up happening. And so, we get closer to that aspect. We won't see it right now, but if I had the other part there, we would. I'm going to primarily focus on this process for trying to find out what our T star is. So we're going to use in our calculator. We're going to do second vars and then option 4, and that's going to give us what's called an inverse T is what it's going to give. And the inverse T, we got to type in an area, and we have to do a degrees of freedom. The area is the same thing we've done before with the inverse norm, 1 minus whatever our percentage is divided by 2, and that's the area in our tail. And then our degrees of freedom, we're always doing sample size n minus 1. So now this calculator, this kind of way our book sets it up, they actually go ahead and tell us what the degrees of freedom are. They don't tell us that our sample size is, like in this case, 26. So it says find the t-value such that the area in the right tail is 10% with a 25 degrees of freedom. So I'm going to show you how to do it on the chart up here because I can go up to 25 degrees of freedom. So what I would do is I would go to the line that says 25, and then I would go across until I get to see where it says a tail is 10%, 0.10. Well, that would be 0.10. That would be this column right here. So the number, my T star, would be 13. Would be my T star in this case would be a 1.316 is what it ended up being. If I was using a calculator and I was doing the calculator approach, let me get out of there, and I go through and I hit second vars, option 4. My area is 0.10, and then again, the degrees of freedom is 25. And there is my 1.316. Remember, we dropped the negative signs on our confidence intervals when we're grabbing our T-stars. We keep the negatives when we end up doing like hypothesis testing when we're doing things, but in this case, we drop them for the confidence interval parts. So now we just matter of practicing each one of these. Again, if I wanted to practice the next one, doing it on the paper, which is sometimes what the online program has us do, where we have to click on their paper. So we go to degrees of freedom of 30, and in the right tail is 0.05. And so again, it really doesn't matter right tail, left tail, because we got to remember that this thing is symmetric. The T distribution is symmetric, and so even though they're saying in the right tail there's 0.05 of the areas over here, well, you know what? Same thing's over on this side. The only difference is it's gonna be more of a negative numbers here. So let's go ahead and grab on our calculator here. 05 would be this column right here, and 30 degrees of freedom gets me to this last dark gray section. So that looks like I just crossed it out right there. So let's take a peek. Cross it out. 1.697. 1.697. And then, so find the T value such that the area to the left of the T is 0.01. Again, this again talks about our symmetry here. Again, we're still just going to go down and go to 18 degrees of freedom to that line and go to the 0.01 column. So 18 degrees of freedom, 0.01, that's the 01 column. 2.552. So 2.552. All right. And then now they said here's another way they phrase it. They say find the critical t value, which is our t star. That's what I refer to as the t star. That corresponds to the 90% confidence interval. So in this case, I need to go through and I need to say, all right, I need to do 1 minus 90% divided by 2. So that would be 0.10 divided by 2, which is equal to 0.05. And that's my area and my tail. And so now 20 degrees is freedom. So 20 degrees of freedom, 0.05 would be the 1725. Again, same process we would do if we're doing it in the calculator. That'd be 1.725. If I did an inverse T in the calculator, my area would be 0.025, or yeah, 0.02, or sorry, 0.05. And my degrees of freedom would be 20. So, second bars, option number 4, 0.05, and then we said 20 for degrees of freedom. 1.724. So, and again, if we round that to the third place, we get the same thing. 1.7247 rounds to that number there. So that's, again, I would use the inverse T on your calculator, even if the problems in your homework want you to do the otherwise. Some conditions for constructing our confidence interval for means. We need to make sure our data comes from a simple random sample or a randomized experiment. The sample size, this is for an independence clause. If I do 5 times our sample size, is it less than or equal to the population? Which is what we had before in the previous unit that we did. And then here's the part that's different. The data comes from a population that's normally distributed. So sometimes they tell us that it comes from a normally distributed data and they give us the X bar and they give us the S sub X. And so if that was the case, if they give the X bar and the S sub X, and then they state for us that it's comes from something that's approximately normal, then I can go ahead and do it. If they don't give me everything like that, then I have some options for the normal condition. Here is hopefully if we have options of what happens if n is that it is less than 30. And the first option is to draw of that case is if it's less than 30, I draw a normal probability plot, and I'm going to show you where that's on the calculator to see if it looks roughly linear. Then we also do a box plot to check to see if there's any outliers. If the data appears to come from a normal population that is approximately normal with no outliers, then it's reasonable to assume that the t distribution to construct it, the confidence interval, is okay. The second option, this one relies on what's known as the robustness of the construction of the confidence interval. An inferential method is robust if it is accurate despite minor departures from its underlying assumptions, such as the assumption of normality in that we referenced up above. So if our sample is less than 15, if our sample size is less than 15, then we can go through and construct our t distribution for confidence interval. We can go ahead and do this if there's no outliers and the data should not be skewed left or right. And so we'd have to go through and verify that with a box plot. Do we have a nice looking box plot that doesn't show any distortions in it? And they give us some ideas of what we need to look at. If we have a sample size that's between 15 and 30, and we want to try to do our t distribution to construct our confidence interval, we can do that as long as we don't have extreme skewness and no outliers. If we have slight skewness, it's okay. So that's where we'll take a look at some examples here in a bit. For an example, look back at figure 10 in section 8.1 if you want to have an idea. A sample size of 25 was needed for that distribution and that problem to mean to be approximately normal. Hopefully, we get to deal with more of this situation. If my sample size is 30 or more, I can use a t-distribution to construct my confidence interval. It doesn't matter if it's skewed. It's okay. If my sample size is 30 or bigger, I don't have to worry about, I can do it for skewed distributions. It's just when it's less than 30, now I got some issues with skewness. So here is our data that we typed in a little bit earlier. And we got the X bar and we got the standard deviation. And to the right here, this is what we call the normal probability plot. So what they went and did is in L1, they had our data. And then in when we went into our stat plot, we chose the very last graph. So like the first one is like a scatter plot, and then it has eventually like a histogram. Then it has two versions of a box and whiskers. The very last graph, that's the normal probability plot. And so that's the one that we want to use, and we have it graph it, and we try to say, okay, this looks roughly linear, so that's not too bad. Got a little bit of a curve there, but it's not too crazy. And then here's the corresponding box plot with it. Doesn't look like there's any outliers. We would usually see them out to the side as a dot, is what we'd end up doing. Now, we can tell there is some skewness here. This thing is technically skewed to the right. And now the reason why we know that is because how large that box is and this whisker here compared to the other half. So this is telling me that on this part where I'm circling, there's a greater concentration of the data. And that's why it's so close together. Then now the data starts getting further apart from each other as we get the different items, so they start spreading out a little bit more. And again, we can do that if we listed these numbers from like in numerical order. Then we'd be able to tell that there was a lot of numbers or a greater frequency of numbers between 25 and 27. And then it started, there weren't as many that much bigger than that. So that's why it's spread out. So here they want us to look at this example here is to kind of go through and decide based on my sample size of 15, would it be appropriate based on the normal probability plot, would it be appropriate to do this? And also on the box and whisker plot. Do I, between the two things, should I do it? They tell us that there's a correlation of 0.893, which tells us that we have a moderately strong positive linear relationship and stuff. But as I look at it, we do have it is curved. So I like right in this part here, it's not a nice perfect linear situation here. It is shows there is some curvature here. So there is some curvature. I do see a couple outliers here. So now the reason why I say there's some curvature, well, the reason why there's curvature is because we got some skewness. Here's where I see some skewness take place. So to me, with our sample size of being 15, I see some skewness. I definitely see outliers. I would say we don't meet normal condition. So that means that we don't go ahead and do a confidence interval for this. All right, next one here. Again, if I draw on the next one, 13, I got a stronger correlation here. Now, do I have a heavy skewness? I don't really have heavy skewness. We might say this is a little bit of slight skewness. Slightly skewed, but not too bad. Now, as I look at this, we see an outlier. And then this one, based on what we have here, here's kind of a weird thing here. We have a short whisker and a long whisker. Wider box, shorter box. So, so that's why I'm saying that we have some slight skewness going on there, but we don't have really, it's hard to say, what's going on because the smaller inside box means I have a lot of frequency there in that area. But then there's a gap over in this whisker. There's not a big gap here, and then there's a big spread here. So it's kind of hard to say, well, hey, is this skewed left or skewed right? Because these two things kind of, this part and that part kind of contradict each other. So with that in mind, I'm going to go ahead and say no, not normal. Just because I do have that outlier. I'm dealing with something less than 13. I got some crazy kind of skewness going on by the box and whisker plot, even though it looks like I have some slight skewness on here and then this part right here. So I probably shouldn't do it. Next one right here. No, this one here. This one looks really nice. Nice pattern, strong correlation here. Notice how that R value. We do have a small sample size, so we got to be pretty, right almost on perfect on what we're doing. Really, with this in mind, my whiskers look about the same length. And there's just a slight difference inside the box, but not too great. So I would say that this is approximately normal. And that's about the best you're going to get with a sample size of being at 9. This one worked out pretty good for what's going on there. So now they asked us to determine the point estimate of the population mean and margin of error for the confidence interval. And here's your upper and lower bounds. And we did this in a previous unit where I told you that if we want to find the point estimate, we can take the upper bound plus the lower bound and divide it by 2. To find the margin of error, I take the upper bound minus the lower bound and divide by 2. So all we're doing here is we're just trying to figure out, okay, we know the two numbers that make up the confidence interval, 18 and 24. That's my confidence interval. So now I just need to go through and say, okay, what's 24 plus 18 divided by 2? 42 divided by 2 be 21. So there is that's my X bar. X bar is equal to 21. And again, why is it X bar? Well, we're dealing with mean. And so I went down. Let's try that. Let me go back and rephrase that. We'll just leave that as point estimate. We won't classify it as one of the other things. What's my margin of error? Then we just go 24 minus 18 divided by 2. So 6 divided by 2 would be 3. That's my margin of error. All right, so now we get a few more of those to practice. Point estimate. And again, if you want to pause, do the rest of these, then turn it back on. Go ahead. I'm just going to go ahead and finish up that the way they're there. So my point estimate would be 25. My margin of error would be subtract divided by 2, which would be 5. Then here my point estimate would be 23 plus 5 divided by 2, which is 14. Sorry, 18, 19, 14. Yeah, 14. And then my margin of error, 23 minus 5, that would be 9. And last but not least, point estimate, 35 plus 15 divided by 2, which would be 25, because 50 would be divided by 2. Margin of error would be 35 minus 15 over 2, which would be 20 divided by 2 is 10. Would be the margin of error. So now they say a simple random sample of size n is drawn from a population with a normally distributed. The sample mean, x bar, so x bar is equal to 108. And they asked us to calculate, so x bar is equal to 108. The standard deviation, S is equal to 10. Construct a 96% confidence interval, and I have a sample size of 25. Now, in this case here, they do tell us that it's normally distributed. So that means I don't have to worry about checking that normal clause since it's 25 or less. They do tell me it's a simple random sample. from a population. I'm going to have to assume that it's got to be a big population here. So how do we find it? So what we can do here, I have a 96% confidence interval. I'm going to show you one by hand with the formula, and then I'm going to do the rest in the calculator. With that in mind, I need to find what is my T-star. What is my T-star for a 96% confidence interval? So I would go inverse T. My area is 1 minus 0.96 divided by 2. My degrees of freedom would be 25 minus 1. Notice they gave us sample size. They didn't give us degrees of freedom, so we have to subtract 1 here when we're using this. So inverse T, 1 minus 0.96 is 0.04 divided by 2 is 0.02. Degrees of freedom is 24. And that gives me a T-star as I get my calculator over here. And we'll go down to inverse T, 0.02, and we said 24. And 2.172, 2.172. And then now I'm ready to do this by hand. Again, my formula for by hand would be my point estimate plus or minus my T-star, and then it's times the standard deviation divided by the square root of the sample size. So this would be X bar is my point estimate. So we said they told us our mean was 108. So 108 plus or minus the 2.172 that I found times, they tell me that the standard deviation is 10 divided by the sample size, square root of 25. And then this would be 108 plus or minus 2.172 times, that'd be 10 over 5, which is 2. So times 2. Then we would do 108 plus or minus 4.344. And then, so as I add, if I add on the right side, I would do 108 plus 4.344. On the other side, the lower bound would be 108 minus 4.344. And so my final would be 112.344. And then 108 minus 4.344. So that'd be 103.656. So there's my confidence interval. And again, we can do the same thing in the calculator. If we go into the calculator, we go stats, over to test, and we're going to be doing what's known as a t-test, is what this is known as. This, oh, sorry, not t, a t-interval. Sorry, t-interval. So if I go down to option 8, I have two options. I have data and stats. We use data when they give us a list of values like we had in the very opening of this lesson. We use stats when they give us statistics, and that's what they gave us. They gave us X bar, and they gave us S sub X. So here I go in and say, okay, what is my X bar? We said it was 108. My S sub X, they said, was 10. There was 25 in my sample, and I'm doing a 96% confidence interval. Go down to calculate, and there is the interval that I have right there. Okay, and I'm going to use that method for the rest of what we're doing here when I need to. Construct a 96% confidence interval for mu if the sample size n is 10. How does decreasing the sample size affect the margin of error? So they want us to use the same mean. They want us to still use X bar, and they want to use the same S. So X bar is equal to 108. Our standard deviation is 10. But they want us to change the sample size to be 10 instead of 25. So let's use our calculator. Stats over to test, down to t interval. And again, I'm using stats. Only thing I need to check here is or change is the sample size to 10. And my interval is 100.42 to 115.58. Now I'm going to write above that on the previous 103,656, 103,656, and then it was 112.344. So, and they asked us the question is, how does decreasing the sample size affect the margin of error? Well, if you're not sure, to me it increased because we got wider. Our interval went from 103 to 100 on the low side, and it went from 112 to 115 on the high side. So to me, lowering sample size makes the margin of error larger. It increases it. Now, why does it increase it? And this goes back to, this is some of the benefits when you end up doing a confidence interval by hand. The only thing we changed was this last part here, 10 divided by the square root of 10. So this was 10 divided by 5. This would be 10 divided by about 3.1. When I divide by a smaller number, I get a bigger answer, is what ends up happening. So that's why our margin of error got bigger, because this part here that I'm circling, which is called the standard error, that got larger, which in turn made the margin of error larger. So decreasing the sample size makes your margin of error bigger, which means you have a bigger confidence interval. If I make my sample size larger, I make my margin of error smaller. Therefore, I have a smaller confidence interval. Next part, it asks us to go through. It says construct a 90% confidence interval. Go back to using a 25 for the sample size, and then compare our results. So we want to compare our result to our 103.656 to 112.344. And all I want to do now, that was my confidence interval, that was a 96%. I want to do a 90% confidence interval using that 25 for the sample size. So let's go stats, over to test, down to option 8. And then 108, sample size, those stay the same. I'm going back to a 25, but I'm changing my margin of error to be 0.90. Now let's see what that does. So my new confidence interval is 104.58 to 111.42. So for me, what this looks like, we went from 103 to 104, which means, yeah, the number got bigger, but actually the lower bound got bigger at the same time the upper bound got smaller. So we ended up actually making our confidence interval smaller. So our confidence interval got smaller. Our CI got smaller. So margin of error got smaller. When n increased. So could we have computed the confidence intervals in A through E, so A through C, if the population had not been normally distributed? Why? No, we probably shouldn't have, because again, since all of our sample sizes were less than 30, we would need to go through and actually look at the data, see if we have any skewness, any outliers. So no, we shouldn't have. No, because sample sizes were less than 30. So would have needed to graph And again, when we're talking about graph, we're talking about looking at the box plot, and then also looking at the normal probability plot, and trying to see if I have outliers or skewness. That's what we're referring to there. I'm going to pause the video now, and then I'm going to come back and do another video for a bunch of more problems here.